Okay, so finally, the hardest question, the extra credit question, question 11. Prove that a finite group cannot be written as the union of two of its proper subgroups. Now this is a very hard question, so a lot of people did not get it, and that's okay, as expected. It's the hardest one, it's the extra credit. It took me a while to figure out a solution to this. Eventually I did find one. And then some of the students that were able to solve it came up with solutions that were shorter and better than mine, in my opinion. So here are two fantastic solutions from students. Number one, you have the Lagrange's theorem technique. So it says, so you know, the idea is we got a group G, which is the union of two of its subgroups. So A and B are proper subgroups of G, so they're both smaller than G. So how big? Excuse me. So how big are they exactly? They are not as big as G, so they're smaller than that. And then by Lagrange's theorem, we also know that they got to be a factor of G. The orders of them, of A and B, have got to be factors of the orders of G. So the biggest possible factor that you could possibly have would be this, right? The best you could do is if G was even and half of it was a factor. That's the biggest that a proper subgroup could possibly be. Of course, you could do better if it was equal to G, but that's different. Then it wouldn't be a proper subgroup. So that's the biggest that it could possibly be. So I really shouldn't say equals. I should say it is at most that. And the same thing is true for the size of B. It is at most that. Now I wonder, what is the size of the union of them, right? Well, that's supposedly equal to G, but I know that the union ought to be the size of the union ought to be the size of A plus the size of B, don't know why I wrote B like that, minus the intersection, right? So that is a fact about finite sets. And so we know that A plus B, excuse me, that this could be at most G over 2, and this could be at most G over 2. So far that's looking good, right? That could be the whole thing, which is what it's supposed to be. But the problem is there's at least one thing in the intersection, right? They at least have the identity in common. Any two subgroups of G at least have the identity in common. So yeah. So the problem is the identity section is not empty. At least has one. So so yeah. So we're gonna get size of G minus 1. So we find out that the union of A and B is small. Excuse me. Smaller than or equal to the size of the group, right? So size of the group minus 1. So in other words, A union B, the size of that is less than, it is not equal to size of G. So there's no way then that these are equal. Definitely not. So there you go. So that's one way to do it. Another way you could visualize that same thing is you're saying, if here's the full thing of G, and the idea is, well, maybe G has proper subgroups, which the biggest they could be would be half of it, like this, A and B, where each one is half, but they can't both. But then they'd have to be both disjoint halves, two disjoint halves, but they can't be disjoint because they both have the identity. So there's got to be a little bit of overlap, which means there's got to be a little bit missing. That can't be the full thing. So yeah, that is the Lagrange's theorem way to go about it, something like that. There's also another way to go about it, which I'll just switch over to the students here. And this way uses only set theory. It doesn't even, or wait, well, not really. I say set theory. Maybe that's the wrong way to say it. But it doesn't use Lagrange's theorem, doesn't use any fancy much of anything. So here's the idea. You say, assume that a group G, there it is, assume that a group G is A and B, union of A and B. So G is equal to the union of A and B. Well, they can't be inside of each other, can they? Right? Because if one was inside the other, then the union would just be the bigger one, and then that's supposed to be all of G when it's supposed to be proper. So no. So they got to be they both got to have things that are not in the other, A and B, which is exactly what they're saying here. So you can say something like this: let A be a thing which is in A but not in B, and same deal, let B be a thing which is in B but not in A. So then, what about the wait? What are they saying here? B is A inverse AB in A. Oh, okay. So well, I'll come back to that. So AB is in the union, right? So saying let A be in here and let B be in there. Well, then AB is in the union. Now, why is that? Because these are both in G, and so G is supposed to be a group, so it's closed under multiplication, and G is equal to the union. So there you go. So AB is in the union, which means it's in one of these. So one of those things is true. Either AB is in A, or AB is in B. Now they say since A inverse is in A. I don't know about that. I mean, that just follows from this anyway. So then finally, why can that not be true? Because check it out, if you have, maybe they should have written this, if AB is in A and A is in A, well, hang on, that means maybe this is what they were saying over here. Yeah, A inverse is in A, and that means A inverse AB is in A, right? Since that's the product of this, and that's the product of two things in A, which is a closed subgroup. So A inverse times AB should be in A, and that's just B. So it turns out that B is in A. Contradiction. Excuse me, geez. Contradiction. Why? Because we specifically assumed that A was not in B. And we were able to do that because we knew that they definitely had some stuff that they didn't both have. So yeah. So we started with A being, we started with A, and it was in one but not the other. But then it turns out it's got to be in both of them. So boom, contradiction. So this whole setup, you just can't have this setup. You can't have two subgroups, two proper subgroups, union together to make the full group. Impossible. Okay, and then finally the final question, is this true for three proper subgroups? So this person did not answer that part. Let's take a look at this other person who did it more or less by the Lagrange method. They wrote it out a little bit differently to me, but that's fine. And ultimately, they came to the same conclusion that if you got two of them, the biggest they could be is each of them be half the size, and so there's no. But that can't happen because they have to have something in common. They gotta both have the identity at least. So yeah. Now, can you come up with an example where you got three subgroups that or union together to make the whole thing? And the answer is yes. And this person has a fantastic example. The Klein 4 group. Indeed, if you take just that subgroup and that subgroup and that subgroup and you union those together, well, together, of course, that's the whole thing. So boom, there you go. And then they also wrote it another way using its isomorphism, if you want. So yeah, so there you go. So there's an example of a group where three proper subgroups, union together to make the full thing. So the claim is not true, right? So prove that a finite group cannot be written as the union of two of its proper subgroups. Yes, that's true. Is it true for three proper subgroups? No, it is not. It is possible to union three together to make the full thing. It's not possible ever to union 2 together to make the full thing. Okay, and that's that. Hope you